Hello and welcome back. We are in our discussion of Chapter 16 dealing with waves and oscillations. So continuing our discussion on properties of waves, just on the top here I've kept what we had in the last video, and that is the definition of a wave. A wave is a disturbance that transfers energy from one location to another. It's important, I think, to expand upon that. The medium that carries the wave from one point to another doesn't move along with the wave itself. The medium's just simply oscillating up and down, transporting the energy. You can see that when you have, for example, a leaf on a lake and you throw a rock to create a wave, and as that wave moves and reaches the leaf, that leaf will just simply move up and down with the wave. It will not travel with the wave. So the medium itself does not get transported. The medium just simply is oscillating up and down. The energy is what is transported from one point to another. In addition, with the exception of the electromagnetic wave, gets the symbol EM, waves require an external medium to transport energy from one location to another. So, in this video we want to focus in on superposition and interference. And I've drawn a couple different scenarios. One is constructive interference, and another one is destructive interference. So I've got two waves here for the constructive interference, wave 1 and wave 2. And I've noted here that the wavelengths of 1 and 2 are the same, and also the periods are the same. So you can see here that the crests and troughs are lining up for waves 1 and 2. Wave 1 has a crest in time and space, where wave 2 has a crest in time and space. Notice that on the horizontal I have time and space. In addition, the troughs are lining up. So if these two waves, lambda 1 and lambda 2, exist in the same space at the same time, with crests that overlap and troughs that overlap, what we see in that space and time is just the sum of the two waves. The amplitude of this wave that has the same frequency and same period as wave 1 and 2 will now have an amplitude that is the sum of wave 1 and 2's amplitude. This is called constructive interference. Juxtapose that with destructive interference. Destructive interference, we're still saying that the wavelengths are the same for wave 1 and wave 2, and the periods are the same for wave 1 and wave 2. So here I've drawn A1. You can see that A1 has a crest initially. It's cycling up from the vertical. And A2 is cycling down from the vertical. So the crest for wave 1 is overlapping with the trough for wave 2. And you can see that that continues to happen, that one wave's crest aligns with the other wave's trough. This is called destructive interference. What you see, and again, this is space and time on the horizontal. What you see if these two waves are coinciding in the same space at the same time, with one's crest aligning the other's trough and vice versa, is a wave of the same frequency and period whose amplitude is the difference of the two amplitudes A1 and A2. You would see nothing in this space and time, or completely destructive interference, if A1 is equal to A2. So if A1 and A2, if these two waves have the same amplitude, and one's trough is coinciding the other, one's crest is coinciding the other's trough, we would have a complete cancellation, and we would see nothing at the location where the two waves are coinciding in space and time. If the amplitudes are different, then we see some diminished amplitude with the same frequency and period. So this is interference, or the superposition, meaning you're placing two waves in the same space at the same time. That's superimposing, superposition. The last thing I'd like to touch on in this video is what's called beat frequency. So that's over here on this side of the board. Beats. So if there exist, remember this backward E means there exist. If there exist two waves which are close in frequency, these are not the same frequencies, but they're close in frequency, F1 and F2. An example would be like 50 hertz and 60 hertz. Those would be two waves that are close in frequency. An observer will hear a beat frequency, if these are sound waves, which is all we're going to be worrying about. An observer will hear a beat frequency, F sub B, which is given by the absolute value of the difference in the two frequencies. So if F1 is 50 hertz and F2 is 60 hertz, then the beat frequency, FB, is 10 hertz. So that gives you an example of how you would calculate the beat frequency. It's pretty easy. And notice you can't have a negative frequency. So if F1 is smaller than F2, then these bars make sure that you're getting some positive value for the frequency. Why are you hearing a beat frequency? Well, it's due to the resulting oscillation of the sum of A1 and A2 at different points in time and space. So as the waves are oscillating, the amplitude at one point in time and space is changing as a function of time. And it's that changing in amplitude that you are hearing as the beat frequency. So we will listen to a beat frequency in class so that you can hear what that sounds like. Or you could do a quick search on YouTube. And a search on YouTube would also give you some examples so that you can hear what the beat frequency sounds like. So we will pick up here next time. Thank you.